Hello again. This is Math 1220 coming to you from the College of DuPage, and the title of this lecture is Logic 2, Truth Tables. As always, please be an active learner as you watch this video. We're now going to introduce some simple rules for doing logical calculations that were developed by George Boole and other 19th century mathematicians. We're going to show how to use truth tables to determine when compound statements are true or false. And later, we will show how to decide exactly when different looking logical forms, such as negation P and Q, and negation P or negation Q, convey exactly the same meaning. Now, some good advice looking forward: truth values for statements using connectives such as not, and, or, and if, then are sometimes slightly different in mathematics than in everyday usage. It's important for you to understand these differences. Let's begin by talking about truth tables by talking about the definition of negation. And you want to memorize these tables just like you memorize your multiplication tables in order to multiply numbers without a calculator. So this is how it works. We're going to talk about P and negation P. And under P, we're going to list all possible truth tables for the statement P, which is true and false. And under here, we're going to say what is the definition then in terms of truth tables of negation P. And what we see is if P is true, not P is false. If P is false, not P is true. So this is the truth value for negation. Let's apply that to this example where we're finding the truth value of negations. Determine whether each of the statements is true or false, and then state its negation. Notice how the negation of each statement has the opposite truth value of the original statement. Let's start with statement A. The Dallas Cowboys are a well-known football team. That's a true statement, and therefore its negation, the Dallas Cowboys are not a well-known football team, is false. The second example is Mexico is a prosperous country in Asia. Mexico is not in Asia, so this is false. That means negation is true. So since the statement was false, the negation, Mexico is not a prosperous country in Asia, is true. We now turn our attention to the AND connective. Remember, the AND is the upside down V. And this works in logic just as it does in everyday life. Suppose you made the following statement to a friend: I'm a basketball fan and I like rock music. Well, that means that you like rock music and you are a basketball fan. So that means the only time P and Q is going to be true is when both P and Q are true. Otherwise, it's going to be false. And notice here the truth values that are possible are P can be true. So there are two states of nature: true, true, false, false, true, false, true, false. This takes into account all the possible ways that P and Q can be true or false. And this is the answer to the problem out here. Again, you want to memorize that a conjunction is true only when both P and Q are true. And you want to be able to fill out this truth table, memorizing it just like you memorize your multiplication tables. Let's apply these learnings to example 2, finding the truth value of conjunctions. Determine whether each statement is true or false. Okay, so J.K. Rowling is a well-known writer. She wrote Harry Potter, and U2 is a famous rock band. Both of those are true, so this statement is true because the only time a conjunction is true is when both component statements are true. Shaquille O'Neal plays first base for the Atlanta Braves, and he refuses to do TV commercials. Well, Shaq never played first base for the Atlanta Braves, and he does a lot of TV commercials. So he doesn't refuse, and so that means that both of these are false. And that means, by the fourth line of my table I made before, this is false. Number C. When you are 50 years old, you will be a billionaire, and Maine is larger than California. Of course, we don't know if you'll be a billionaire by age 50, so P is either true or false, and we don't know which. However, we do know that Maine is not larger than California. Therefore, we're dealing with either line 2 or line 4 of the figure. But in either case, the statement is false, because the second statement is false. We're now going to turn our attention to disjunction. And we're going to find that a disjunction is false only when both of its component parts are false. Again, you're memorizing this. Okay, so here is the truth table for disjunction. Again, a disjunction is false only when both are false. Otherwise, it is true. And this is or. And here we list all possible ways that P and Q can be true or false. Now, mathematicians, however, use an inclusive or in this definition. And that means we use it perhaps slightly differently than some people use it in everyday life. So suppose your math instructor announces that there will be a quiz next Tuesday or Thursday. You come to class on Tuesday and have a quiz, then you're not expecting another quiz, so you could cut the Thursday class. Actually, I hope you wouldn't do that. When you return the following week, you find out that you missed a quiz on Thursday as well. You probably feel your instructor misled you. But the real fact is that he used this in terms of an inclusive or. So both could be true, and you still get a true. So know the difference between an inclusive or, which is talked about here, and an exclusive or, which is true only when one or the other is true, but not both. And so notice that this differs from the way we normally define it, but this is the way we define it in this class. So please remember that, just like you memorize your multiplication tables. Remembering that the final column for an AND table has only one true value, and the final column for an OR table has only one false value, might help you do the logical calculations more quickly. Here's an example analyzing the logic of an advertisement. So here's a help wanted ad. Management trainee wanted. Applicant must have a 4-year degree in accounting or 3 years of experience working in a financial institution. So which applicants should be considered for a position if we interpret or to be the way we determine it in mathematically, that it is an inclusive or. So here's someone who has a 4-year degree in accounting but has worked only for 2 years for a loan company. Well, that's going to be true, so she should be considered as a job for the job. Heidi studied accounting in college but did not graduate and has worked 5 years for another company. Well, she still can be okay because her credentials are reflected in line 4 of the figure. But that means she's not qualified because neither one of these things is true, because she's only worked selling electronics, not worked in a financial institution. Monty earns a 4-year degree in accounting and has 5 years experience for a credit card company, which is considered to be a financial institution, and so he should be considered. And here we note that because set theory and logic are both examples of Boolean algebra, they have similar structures, and these correspond. And corresponds to intersection, or corresponds to union, not corresponds to complement, and if then corresponds to is a subset of. We did not study this in the class, so you're not going to be tested on set theory in this class. Let's look at another example. Now here is a common thing because we'll be looking at a compound statement, more complicated, and you're supposed to fill out the truth table. So we want to find the truth table for negation P and Q or P and Q. And it's important that you realize that those parentheses make a difference because you do what happens in the parentheses first. So you're going to calculate these first. So first you list all the possible truth values for P and Q here. Then not P is going to be false, false, true, true. And then not P and Q then are going to be true only when both are true. It's going to be false otherwise. P and Q we know is going to be true only when both P and Q are true and false otherwise. Now we're considering the OR of these final two columns. And this is going to be false only when both are false. So that's going to be here and true otherwise. And again, the answer is the final truth column for the entire expression. So this would be the answer to the question if I were to ask you this question on a quiz or a test. Now, it's possible for us to have more than two variables where we had 4 rows. We could have 3 variables. Now, P can be true or false, and independently Q can be true or false, and R can be true or false. So it's 2 times 2 times 2, or a total of 8 possible truth values. And in general, notice how each time we add one variable, each branch in the previous tree splits into 2 branches, one for T and one for false. So in general, the following pattern is true. The number of lines or rows in a truth table, if the statement has K independent statement variables, then its truth table will have 2 raised to the K power lines. So if it has 3, it has 3 variables, we will have 8 lines. If it had 4 variables, it would have 2 to the 4th, or 16 lines. 5 variables, it would have 2 to the 5, or 32 lines, and so on and so forth. Here we're doing a calculation of this truth table. So we want to calculate what is the truth value of not P or Q and not R. So here, and the easiest way to get all 8 combinations is to go 4 T's, 4 falses, 2 T's, 2 falses, 2 T's, 2 falses, and alternating TF, 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 TF. And we will get all the possible 8 combinations here. So if I do that, then I'll find that negation P is going to be false, 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 followed by all trues. Negation P or Q is going to be, and I'm looking at this one, or this column. I will get true, true, false, false, true, 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 true. When I look at not R, it's the opposite truth values this. So this is going to be false, true, false, true, false, true, and false, true. But now I combine them by taking the and of this column with this column. Now, this is an and, so the only time that's going to be true is when both are true. So it's going to be true here, here, and here, and it's going to be false otherwise. Again, the question I'm going to ask you is, I will give you this, and probably these assignment of truth values, and ask you to come up with this column. We're now turning our attention to logically equivalent statements. It is important to know when different looking statements express exactly the same information and when they don't. We compute truth tables to decide if they have the same meaning. That means they have the same final truth column. So 2 statements are logically equivalent if they have the same variables, and when their truth values are computed, the final columns are identical. Okay, so here is an example determining when they mean the same thing. Suppose I say it's not true that the pasta bar accepts coupons and the deli accepts coupons. Well, that is going to be negation P and Q, and I compute negation P and Q over here. You should check to make sure you follow this entire calculation. But for B, the words are different. It says the pasta bear does not accept coupons, or the deli does not accept coupons. So that is negation P or negation D. And here's the truth value for those. But notice that the final truth column for the same assignment of variables here is going to be false, true, 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 false, true, true, true. That means those 2 statements are logically equivalent. In fact, we have a theorem that is called De Morgan's laws. And De Morgan's law says that negation, parentheses, P and Q, is logically equivalent to negation P or Q. You can kind of think of this as the distributive property. Note that the negative is distributed to both the P and Q, but the negative changes the conjunction to a disjunction. Similarly, negation P or Q is logically equivalent to negation P and negation Q. These are De Morgan's laws, and sometimes you can use these in simplifying problems. And we can apply this logic to legal document. So here's the following statement. It is false that if you received interest from a seller, financed mortgage, and the buyer used the property as personal evidence, then you cannot use that for like a tax deduction. But it's easier to rewrite this if we say, because we have it's false that, so you can say that this is not used in Morgan's law, and we will get, and again the original one is negation R and B, but now we will distribute this the same thing as negation R or negation B. So you did not receive interest from a seller financed mortgage, or the buyer did not use the property as a personal residence. Some more good advice. When you're using logic to rewrite a statement, the result can sound awkward. You may want to smooth out the grammar so the statement sounds better. But this is usually a mistake. Unless you're quite careful, you can change the meaning by rewriting it. In logic, the form of the statement is more important than its literary style. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We are all in this together. May God bless you all.